Join with computer. Yes. Okay, now for the second hour, we have yes, we have the interference. We are going to talk about the interference in the cellular communication system. Of course, to understand the interference, we have some terms. First of all, we have to be familiar with. Then we are going to discuss the interference. Now, let's make a slideshow. Yes. First of all, we have to distinguish between the noise and interference, okay, in order to be able to minimize the effect of interference, especially co-channel interference. In common use, the noise is defined as what? Means any unwanted signal. Noise means any unwanted signal. In both analog and digital electronics, noise is an unwanted perturbation to a wanted signal. It's called noise as a generalization of audible noise heard when listening to a weak radio transmission. This is what about the noise. Signal noise is heard as acoustic noise if played through a loudspeaker. So, or it can be like a snow on a television or video image. This is what the noise, and the noise will be uh, an enemy for the communication system. Now, if we are going to talk about the noise in the signal processing or computing, it can be considered as unwanted data without meaning. That is data that is not being used to transmit a signal, but simply produced as an unwanted byproduct of other activities. This is what? This is the noise. Now, let us define what? The interference. Interference in the wave propagation in physics, the superposition of two or more waves resulting in a new wave pattern. Look, now when we talk about interference, we don't have weak signals. So one difference between interfering signal and noise signal is it will be what? Will be a weak signal. Okay, I mean the power of the noise will be less than the power of the signal. When we talk about the interference, we have two strong signals. Interference in communication, in telecommunication and electronics, anything which alters, modifies, or disrupts a message as it travels along the channel between source and receiver, or source and destination. Typically, the term refers to the what? To the addition of unwanted signal to the useful signal. Look, please, both of them are what? Are signals. I mean, both of them are strong signals, not weak signals, as in the case of noise. Now, interference is the major limiting factor in the performance of the cellular radio system. Of course, if you are going to increase the capacity of the cellular system, one of the most important parameter which affects or limits the number of users in the cellular communication system will be the interference. And basically, we have co-channel interference. Sources of interference include the following: another mobile in the same cell. Well, a call in progress in a neighboring cell. Other base stations operating in the same frequency band, I mean co-channel cells. And a non-cellular system which which leaks, okay, energy into the what? Into the cellular frequency band. Oh, now point number four really is a very important one, okay? any non-cellular system which may what? Which may leaks energy into the cellular frequency band. Really, how such a cases will occur? I mean, point number 4. Now I will show you what do you mean by this point. uh, as you know, to transmit communication signals, we are going to use power amplifiers. As I think you have heard about the amplifiers, for example, we have class A, class B, class C amplifier, and we have class D amplifier. Um, there are 3 regions for the operation of amplifiers. Say we have linear region, okay? Amplifiers will work as the following. For example, linear region. In the linear region, V out equals to A by Vn, okay? This is linear region. Why? V out and Vn relation between them is a constant, okay? Again, we have a cutoff region. At the cutoff region, the current will be 0. And we have a saturation region. Of course, we are going to move the Q point or the operating point of the amplifier or the transistor near the saturation region. Why? To provide good amount of current. In other words, providing large amount of power. So in the saturation region or near the saturation region, the relationship between V output and V input becomes nonlinear. Of course, what do you mean by nonlinear? At that time, V out equals to, for example, say a constant A multiplied by Vn squared or Vn cube, Vn to power 4, and so on, okay? When the relation between input and output becomes nonlinear, I mean V out equals to A multiplied by Vi square or Vi cube or Vi to power 4. This cases represents nonlinear relationship between input and output of a given amplifier. Now, someone may say, and so what's the problem? Look at the problem. Now, assume that Vn is equal to AC cosine omega CT. Okay. Now, this will be the carrier signal. Okay. We are going to transmit this signal, but after passing this signal through the power amplifier, and then we are going to use an antenna to transmit the signal. This will be power amplifier. Power amplifier. Now, what will happen? Look, please. We said that the relation becomes nonlinear. So, V out equals to A multiplied by cosine omega CT all squared. And you know, cosine squared theta, for example, cosine squared theta will be what? 1 over 2, 1 plus cosine 2 theta. What does it mean? It means that V out will be A over 2 multiplied by 1 plus cosine 2 omega CT. Actually, we have feed the power amplifier by cosine omega CT. And it produces what? Produces cosine 2 omega CT. Of course, cosine 2 omega CT will lie where? Outside the interested band. And it may lie where? In the nearby services. Okay, so such a terms or intermodulation terms will lead to what? Will lead to interference to the other services. Of course, we can expect that other service again will what? Will leak unwanted energy into the bandwidth of the cellular communication system. Oh, what's going on? Okay. Now let's go to the PowerPoint slides and to continue. Okay, now can you see the slides please؟
بله دكتور.
درسته. ما مشكلة هيك بالاكونت نظام تجيبه براستي Okay. Now we have talked about the sources of interference. Okay. Now we are going to talk about the effect of interference on the cellular communication systems. Of course, as you know, we have two kinds of channels: control channels and the traffic channels or voice channels. Control channels are responsible for what? Call initiation and call setup, okay? While the voice channels will be used, for example, during the conversation. Now, interference on voice channels causes crosstalk, where the subscriber hear interference in the background due to an undesired transmission. So this will be the effect of interference on what? On the voice channel. On the other hand, we have another effect on the control channels. Interference leads to missed and blocked calls due to errors in the digital signaling. In urban areas, interference is more severe due to what? Due to the following results: the greater RF noise floor, large number of base stations and mobiles in the city center, of course. Interference has been recognized as a major bottleneck in the increasing capacity and is often responsible for what? Dropped calls or blocked calls. Now, up to this point, we have explained what do you mean by interference, and we have compared the interference with the noise. Sources of interference, again, we have explained, and the effect of interference on the voice and control channel. Now, let us talk about two kinds of interference which affect on the performance of the cellular communication system. First one is called the co-channel interference. Really, it will be very difficult to control. Even though interfering signals are often generated within the cellular system, well, they are difficult to control in practice due to what? Due to random propagation effects. Even more difficult to control is the interference due to out-of-band users. In the previous example, we have talked about the nonlinearity of the operational amplifiers, okay, or power amplifiers, which arises without warning due to front-end overload of subscriber equipment or intermittent intermodulation products. In practice, the transmitters from competing cellular carriers are often a significant source of out-of-band interference, since competitors often locate their base station in close proximity to one another in order to provide comparable coverage to the customers. As you know, when we are going to install a cellular communication system, first of all, our first phase is called cell planning. In the cell planning, we are going to study the geographical region carefully, and based on the geographic region, I mean, if you have, for example, mountains, high buildings, and so on, okay, using a program which is intended for the cell planning, we can, using the geographic information system, GIS again, feed to this system. At that time, the program will the program will determines the optimal locations for the what? For the towers or the base stations. Okay, based on the geographic information, we can what? We can determine the best location for the what? For the towers or the cell sites. So the competing companies will locate their towers or base stations in close proximity to one another. Well, co-channel interference frequency reuse implies that in a given coverage area, there are several cells that use the same set of frequencies. These cells are called co-channel cells, and the interference between the signals from these cells are called co-channel interference. As you can see here, in this system, we have 3 clusters of 7 cells, A, B, C, D, E, F, G. Okay, these are 7 cells working together. Again, here we have another cluster, and here we have another cluster. So in this figure, we have 3 clusters. Of course, every cluster has one cell A, okay? So these cells are called what? Co-channel cells. Of course, the same story for the cells B, okay? Here we have 3 Bs. Again, cell C, okay? So in this system, we have co-channel cells. Okay, please look at this important information. Unlike thermal noise, which can be overcome by increasing the signal-to-noise ratio. Now, for example, if you are talking about, for example, a noise signal, we have a noise signal. How we are going to enhance or improve the signal-to-noise ratio? By merely just increase the signal power. Why? Because the noise level is constant, okay? Approximately is constant due to the environment or the channel. Now, so if you are going to enhance the signal to noise ratio, all you need is what? To increase the signal power. This will lead to what? This will lead to enhancing the signal to noise ratio. Now, when we talk about interference, it will be very difficult. Co-channel interference cannot be combated by simply increasing the carrier power of the transmitter. Why? Really, we have 2 strong signals. So if you are going to increase the power transmitter of this base station, again, another base station again will be increased. So increasing the power, transmitted power will not be used to solve the problem. So this is because the increase in the carrier transmit power increases the interference in the neighboring co-channel cells. So this solution cannot be used with the interference. Now, the solution for the interference will be the following: to reduce co-channel interference. Okay, co-channel cells must be physically separated by a minimum distance to provide sufficient isolation due to what? Due to propagation. I mean, in this figure, okay, we have to increase the distance between the A cells, okay, or B cells. Of course, how we are going to increase the distance? By considering larger cluster sizes. For example, cluster size of 9, cluster size of 12, cluster size of 19, and so on, okay? So if you are going to consider larger cluster sizes, the interference will be reduced. But keep in your mind, when you are going to consider larger cluster sizes, this means that the capacity of the system will be decreased. So what we are going to do? Really, the solution is what? We have to make a trade-off between the capacity and the interference or the co-channel interference of the cellular system. And we have to select moderate values for N capital in order to provide sufficient distance between the co-channel cells and provide acceptable capacity for the system. Now, by now, I'm going to what? We are going to derive a formula for what? For the signal to interference noise ratio. We have some assumptions in order to be able to derive a formula by which we can calculate S over I. So let us go to the assumptions that we are going to consider in order to be able to derive a mathematical formula for the S over I. When the cell size of each cell is approximately the same, look, assuming that cell sizes are the same, of course, and the base station will transmit the same amount of power. Well, when you are talking about same cell size, of course, we have what? Same amount of power transmitted from the what? From the base stations. Now, the co-channel interference ratio is independent of transmitted power and becomes a function of the radius of the cell and the distance between the centers of the nearest co-channel cells D. Okay. Now Q, which is the reuse ratio, okay, D over R. D, which is the distance between two co-channel cells, okay, and R represents the radius of a cell, is equal to square root 3n capital. Now, by increasing the ratio D over R, look how we are going to increase D over R. Of course, look at the right side of this equation. Only we have a single variable, which is what? Which is n capital. So if you are going to adopt large values of n capital, at that time the D over R will be enhanced. I mean, the reuse ratio will be increased. And in this way, the physical distance between co-channel cells will be increased. Look, by increasing the ratio D over R, the spatial separation, okay, between co-channel cells relative to the coverage distance of a cell is increased. Thus, interference is reduced from improved isolation of RF energy from the co-channel cell. The parameter Q called the co-channel reuse ratio is related to the cluster size for a hexagonal geometry. As you can see, Q equal to D over R and equal to square root of 3n. Look, a small value of Q provides larger capacity. Why? We said that the equation is square root of 3n. Of course, whenever we are going to use small n, at that time, Q will be smaller, but it means interference will be increased, but the capacity of the system will be better. Whereas large value of Q improves the transmission quality due to smaller level of co-channel interference. A trade-off must be made between these two objectives. I mean, the interference and capacity in actual cellular system design. Look, please, here we have different values of I and j to lead to different values of n. As you know, by following the equation of n capital equals to I squared plus I by j plus j squared. Now, when I equal to 1, j equal to 1, the cell size will be 3. Of course, different values of I and j will lead to different cluster sizes. As you can see, if you are going to follow the equation of this equation, I mean, QD over R squared of 3n, you can see when the cluster size is increased, the reuse ratio will be increased. This means that whenever we are going to adopt larger cluster sizes, the physical distance between co-channel cells will be increased, and hence the interference will be reduced. Now, let us now talk about the co-channel interference formula. Of course, to do so, what we are going to do, we are going to talk about a formula by which we can calculate S over I. To understand this thing, let's go to this figure. Please look at this figure to understand what's going on. Or let me talk about or make a sketches on the whiteboard is better. Real time. Yes. Okay. Look, please. Here we have, say, cell A. Okay. Due to the hexagonal shape, again, due to the hexagonal shape, every cell has 6 co-channel cells in the first tier. What do we mean? Look, 1, 2, 3, 4, 5, 6. Okay, every cell will be surrounded by 6 co-channel cells. To understand what's going on, look please, I'm going to make a zoom for this cell. Just for what? For explanation. But actually they are the same size. Look please. This will be what? This will be the tower of this cell, and inside this cell we have a mobile unit. Okay, now by now the mobile unit is connected to this A cell. Okay, let me highlight it by pink. Okay, now our mobile by now is connected to this uh, uh, base station. Now what will happen? Now the signal which is received from this base station represents what? Represent the interested signal and will be called S. Okay, so the mobile will receive S from this base station. Why? The mobile is connected to this base station. Well, but keep in your mind, other co-channel cells are what? Are transmitting power with the same frequency. Yes, they are aparted away from the original cell or the interested cell, but the energy may leaks inside what? Inside the interested cell. So what will happen? Now look please. This cell will transmit I1, interference 1, okay, to the mobile. This one will transmit I2, interference 2, interference 3, interference 4, interference I5, okay, I5, and this one will send I6, okay. So what will happen? How we are going to calculate S over I? S over I, it will be S, which is the signal power received from the interested base station, divided by what? Divided by interference from first co-channel cell, interference from second co-channel cell, I3, I4, I5, and I6. As I think now it's very clear what do you mean by signal to interference. Okay, this will be the signal of an interference. It will receive the signal from the interested cell, and it will receive interference from other co-channel cells. As you can see, we have 6 interfering signals, and we have a single interested signal S. Now let's go back to the PowerPoint slides. Now, let I naught be the number of co-channel interfering cells, and actually I naught will be 6. Then the signal to interference ratio S over I or SIR for a mobile receiver which monitors a forward channel can be expressed as S over I, S over summation I from 1 up to I naught, I subscript I. Okay, so it means I1, I2, I3, I4, I5 up to I6. Okay, now where S is the signal, desired signal power from the desired base station, as I have told you, and I subscript I small is the interference power caused by the I interfering co-channel cell base station. Now, if the signal levels of the co-channel cells are known, then the S over I ratio for the forward link can be found using the previous equation. Up to this point, do you have any questions, please? Any questions?
الناس هيدا تخش.
Okay, now it's clear what do you mean by S over I. Let's go more in detail. Now, here we have again another important formula. Look, please. Propagation measurement in a mobile radio channel show that the average received signal strength at any point decays as a power law of the distance of separation between transmitter and receiver. The average received power PR at a distance d from the transmitting antenna is approximated by PR equal to P naught d over d naught raised to power minus n. Of course, again, let me show you what do you mean by this equation. Okay, this is a very important equation, really, which is what PR, P received equals to what? P naught multiplied by D over D naught raised to power minus N. There is some delay. Yeah. Okay, now. Here we have a tower. Say 1 meter from the tower will be what? Will be D naught. Okay, so very near to the power will be what? Will be D naught, and the transmitted power, total transmitted power from the tower will be what? Will be P naught. Okay, so if you are going to measure the power at the tower, it will be P naught. Now, when we are going to go away from the base station or the towers, okay, really base station different from the towers. Okay, towers means the location by which we are going to install the antennas. When we are going to move away from the towers, say at this point, of course, by now the distance between the mobile unit and the tower becomes what? Becomes D. Okay, and P received power here will be PR. Well, as you can see, the PR equals to P naught, which is the total power transmitted from the towers. D naught, very very close, for example, to the tower. I mean, in say in 1 meter or at the tower. Actually, we are at the tower measuring the power P naught. D will be a distance away from the tower and PR, and N, as you know, N again will be what? Will be path loss exponent. So in this way, we can what? We can measure the power at a distance D from the what? From the cell site or the tower of the base station. In dB, PR in dBm, of course, you know, when we talk about received signals, of course, when we are working with small amount or weak signals, at that time, we are going to consider 1 milliwatt as the base. And of course, we are going to measure the signal with 1 milliwatt, not with 1 watt. So we have dBm. P out dBm minus 10 log 10n log d over d naught. If you are going to use the say the dB to express the amount of received power. Okay. Now, if di, of course, by now you know what do you mean by di. D capital, I mean the co-channel distance, is the distance of the ith interferer from the mobile. The received power at any given mobile due to the ith interfering cell will be proportional to the what? Di raised to power minus n small. The path loss exponent typically ranges between 2 and 4 in urban cellular systems. Of course, I mean cities. Now, when the transmit power of each base station is equal and path loss exponent is the same throughout the coverage, the S over I formula for the mobile can be approximated as, look, S over I equals to R capital to minus N, which is the radius of the cell, divided by summation I from 1 up to I naught, di to minus N. Of course, here you are using di, d subscript I. Why? Of course, if the mobile lies at the center of the cell, at that time we have the same d's. Yani, d1, d2, d3, d4 would be the same. But if the mobile lie at an edge of the cell or at the boundary of the cell, at that time we have different values for d. Now, if the mobile lies or located at the center of the cell, at that time we can simplify the previous equation, considering only the first layer of interfering cell. If only the interfering base stations are equidistant from the desired base station, and if this distance is equal to the distance d, okay, we said that all equals to d, the same d we have between cell centers, then S over I becomes d over r, which is the square root of 3n raised to power n small divided by what? I naught. I naught represents number of interfering cells. So it will be square root of 3n raised to n small divided by I naught. By now, S over I relates the cluster size n, which in turn determines the overall capacity of the system. So S over I will be the following relation: square root of 3n raised to power n small divided by I naught. Of course, the previous equation will be used what? When we have the same d's. Now, if we have the actual case, say, when mobile unit lies at this point. Look, now here we have again cell A and 6 co-channel interfering cells. Look, now the distance of this A to the mobile will be d plus r. This one again d plus r. These two cells, the distance will be d, while these two cells will be d minus r. So we have 2 multiplied by d minus r, 2d, and 2 multiplied by d plus r. Okay, these are the different distances. Of course, here we are assuming that the path loss exponent will be 4. This is about what? About the relation of the S over I. Next week, inshallah, we are going to solve some examples, numerical examples about the co-channel interference and about measuring the power transmitted from the signal, from the cell, sorry, I mean measuring the interference power, okay? Of course, using the relation of what? PR equal to P naught multiplied by D over D naught raised to power minus N, okay? Do you have any questions, please? I'm ready to answer any questions if you have.
دكتور
بلي كلامك.
شنو بس ار معناه ار كابيتال
شو؟
ار كابيتال يعني شيء بس
R capital radius of the cell.
يعني is given بسعر ذاتي
هذه دي متى؟ يعني بالي خوف بس دقيقة والله كان ليش ما أويدي لسر وايد بورد شيء بس كذا قبل الله. دي بالضبط متى تشتى. اوكي يعني مثلا عفوا okay, this will be what? R capital. Okay, R of the cell, radius of the cell. Okay, any other questions?
دكتور بس أجا مسألة انترنتي حالك دنجد قطع دبي زور
نعم.
يعني والله زور قطع دبي زعاز دبي
اوه اوكي، لا مشكلة ان شاء الله.
يعني والله
يعني دفمن مشكلة ندر كانت دفمن مشكلة كتشتك هو على اساس يعني نظام يعني از نظام. اوكي، على كل قاعد تحكي يعني شو مشكلة لا مشكلة ان شاء الله.
احتمال انترنت ضعيف بدكتور احتمال انترنت
احتمال اوكي
ما
ان شاء
دكتور
الله.
دس خوش
عين دس خوش دار سر عزيز سر. اوكي ان شاء الله. حفتيابت دي وتحلكم كان بيسارك يعني نيوميريكال لسر interference. Okay, thank you and see you next week inshallah.